Thank you. Hello, everyone. I'm very happy to see you guys here today. I'm going to talk about attacking DRM subsystem to gain kernel privilege on Chromebooks. But first of all, let me introduce myself briefly. My name is Shen, also known as Redmi. So my friends will call me Redmi, so you can call me this way as well. I'm a senior security researcher of Keenlab Tencent. I'm based in Shanghai. My research mainly focuses on the kernel vulnerability hunting and exploitation since 2014. And my target device normally is Android, but I also care about any other Linux distribution. This time, I will talk about the Chrome OS. You can follow me on Twitter or follow me on GitHub. My ID has been shown on the slides. By the way, I'm also a fan of console games, anime, and mystery novels. So I'm always a big fan of Japanese culture. Always happy to be here to visit Tokyo and see you guys here. Here is today's agenda. But first of all, let's take a look at the Chrome OS security. What is a Chromebook? So on the picture, you can see there are many different kinds of Chromebooks. A Chromebook may be a laptop or tablet. A Chromebook is running a Linux-based Chrome OS, and there are different kinds of Chromebook and different brands and different models. On the picture, you can see some Chromebook made by HP, Dell, Asus, and Lenovo. There must be some reason for you to buy a Chromebook. First of all, let me say it clearly. It's not for video gamers. The graphic performance is really poor. You cannot buy a Chromebook to play some games like Final Fantasy 15 or something like that. Yeah, but it's still good enough for you to finish the daily work. For example, browsing the internet, chatting with your friends, watching a video, and maybe editing some documents. And one more thing is it's very easy to use. There is no difference between the Chrome OS and the Mac OS on UI, so it's easy to use. And some model can be very cheap. On the picture, there is a Lenovo Chromebook. You can see the price is only 30,000 Nihon yen. It's very cheap, and that may be a reason for you to buy it. But what I really want to talk about is Chromebook is very secure. I have to say a Chromebook is one of the most secure laptop for now because there are some reasons. First of all, there is a Chrome browser. I think most of you will agree that Chrome is the most secure browser for now. So in Chrome OS, all applications are based on Chrome, and there must be a sandbox. Just like Chrome OS has its OS-level sandbox. And both applications and system services are isolated and sandboxed. Another thing is there is a secure file system and secure storage. So you cannot modify the root partition, and the root file system is read-only. And this feature is powered by the verified boot and DRM verity, and we will talk about it later. The last thing is there is an additional Linux security module, the LSI. It is stacked ahead of SE Linux, and it's developed by Chrome team to make sure the file system is secure. Oh, there is another thing, that is automatic updates. So the Chrome team not only fix known bugs on Chrome and Chrome OS as soon as possible, but also will apply security patches to the kernel regularly. So you cannot attack it by exploiting end-day bugs. So let's take a look at the sandbox. So the Chrome OS is using the mini-gel 0 to execute system services. The mini-gel will apply different kinds of restrictions, for example, the user ID, the compatibilities, namespace, a secure computing filter policy, and SE Linux policy. So all these restrictions are based on Linux security features, but nothing is special. But it's very efficient. To bypass the sandbox, it requires additional vulnerability. And for the more details about the Sandbox, you can check the official documents of Google Chrome. So the Chrome OS can verify the boot chain during the system booting up. That is verified boot. Firmware, room disk, and system partition can be verified, and especially the system partition is verified by the DRM verity in the kernel. So DRM verity is a kernel module developed by Chrome team, but now it can be used on Chrome OS and Android. And it can be protected by, it can protect the system partition from being modified, and it will calculate the checksum of every block on disk before I/O operation. So it will crash the whole system if the checksum is wrong. So the system partition, if the system partition is modified by malicious program, the Chrome OS will know that and will enter a boot loop, which means you cannot boot up the system anymore. So to bypass the DRM verity, you need a persistent exploit. So the persistence means keep your malicious process persistently alive across the reboots. However, besides DRM verity, Chrome OS also has multiple features to stop persistent attack. So what have they done for anti-persistence? The first thing is DRM verity. I have given out enough explanation about it. The second one is no execute mount for writable data partition. So the malware in this partition cannot be executed. And another one is the LSM, Linux Security Module. And I will talk about it on next page. And Chrome also have other mitigations for specific persistent exploits in the history. That is because benefiting from the Google Chrome VRP, the vulnerability reward program, Google received many reports on persistent exploits, so they can keep improving the anti-persistence logic on Chrome OS. So for now, let's just take a look at the LSM. LSM is a Linux security module. And this module will reject symlinks that will redirect the system's write action during boot. So it was a regular approach for attackers to make a symlink, which may lead to abusing the system configuration to achieve the persistence. And for the same reason, the LSM also refused to mount a path with symlinks. And it also can provide hardening against the load module and firmware from data partitions, so attackers cannot load untrusted module or untrusted firmware. So that's all about Chrome OS security today, and I'm going to introduce our exploit chain on Chrome OS. So what is a Chromebook? A PWNium is a special program of a Chrome VRP, and Google says that we have a standing $150,000 reward for participants that can compromise a Chromebook or Chromebox with device persistence in the guest mode. And actually, the price previously was $100,000 USD, but for now, starting from this July, it has been raised to $150,000 US dollars. So here is the PWNium requirements. The PWNium requires an exploit chain, includes 3 parts. The first one is a Chrome browser renderer RCE in the guest mode. Mostly, you need to find a V8 JavaScript ng bug to finish it. The second one is a Sandbox escape. And the last one is OS persistence. So you should achieve the OS persistence just to keep the exploits alive across the reboots. So in May this year, my teammates and I from Keenlab Tencent submitted a full exploit chain to the Chrome VRP. It includes 5 vulnerabilities, and the first one is, OK. So I'm going to speak slowly for the interpreter. Yeah, there are 5 vulnerabilities. The first one is CVE 2019-5825. It is an out-of-bounds write in V8 JavaScript ng. And the second one is CVE 2019-5826. It is a use after free in index the database. We use this bug to bypass the sandbox. So the next, there are 2 privilege escalation bugs. One is for kernel mode, and another one is for user mode. The last one, after we gain the root privilege on Chrome OS, we still need another bug to achieve the Chrome OS persistence. So that is CVE 2019-13689. So we use all these bugs to build a full exploit chain, and we use this chain to bypass all other mitigations on Chrome OS. And finally, Google Chrome confirmed the exploit chain, and the chain met PWNium requirements. And this is it's a mail from Google. They just say that we met the requirements and get the bounty. So this is the disclosure process of our chain. So we have already disclosed the first and the second bug on KCon and Black Hat, but for now we are here. We are here on the CodeBlue Tokyo, and I'm going to talk about the third part. It's a kernel exploits found by myself. The CVE number is CVE 2019-16508. And for the last part, actually, it's going to be disclosed on POC So by my teammates Gengming and Melody. And what is my contribution to this chain? I have already said that I contribute kernel exploits. By the end of March this year, so my friend and my teammate, whose name is Gengming, he asked me, so if I can find a kernel vulnerability, or I can make a kernel exploit for the Chrome OS. That is because at that time he already have a V8 bug for the RCE and Sandbox escape, but he don't have a privilege escalation and persistence. So he believed that he need a root privilege to achieve the OS persistence. So he just asked me if I can do that. So I just say, OK, let's see what I can do. So I start my research by the end of March, and the first thing I need to think about is the attack surface. So actually, I don't need to find a Linux kernel vulnerability that can affect all Linux distributions. That may be difficult and maybe takes me more time. I just want an easy job to get the bounty and to finish the work. So I believe that a bug targeted at official Chrome OS hardware will be fine. So because I have only 30 days to finish it. If I cannot, it may be failed. So let's just try to find a vendor bug on specific Chromebook. So here is a partial list of Chromebook models. I'm looking for easy target. So after looking for a while, I found a very good one. That is Lenovo Chromebook S330. But it just came in my eyes because of its platform. So can you see that the platform and kernel ABI here is different with others. It's not Intel CPU, it's an ARM CPU, and it was powered by the MediaTek. The platform model is MT8173, and it may be vulnerable because, I have to say, the MediaTek is always the paradise for bug hunters. You can always find more and more bugs and endless bugs on MediaTek. Yeah. So I just choose this one. The model's name is Lenovo S330, and you can see the picture. It just looks like a laptop, nothing special. And but it has the board name was given by the Google Chrome. It's Hana. It's Japanese words. It just means flower. Yeah, and I like it. So okay, we just confirmed the attacking target, but is it easy to exploit it? Let's take a look at its mitigation on hardware. So this is the main mitigation on the ARM CPU, and let's take a look at what is enabled and which is not. So that is the other reason I choose MTK-based Chromebook, because the lack of the hardware mitigations. So only PAN and PXN are enabled. So they can make some trouble for exploitation, but it's not a very big problem. We are very experienced to bypass it and achieve the kernel code execution. So, but the other mitigations, you can see the UAO, the KSR, and many other things. So for example, PAC or some other things are not enabled. So in summarize, it's very easy to exploit. So what's next? So we have to do some analyze, and we know it's easy to make it. So I just bought a Lenovo S330 from Amazon UK, and I need to wait 2 weeks for the global delivery, because the delivery from UK to China, it takes some time. So I just wait. But during my wait, I can do something like think about which part of the code may be vulnerable. So finally, I found a good one. It is a direct rendering manager, that is DRM. So let's talk about the direct rendering manager. It's a subsystem of the Linux kernel, and you can see the source path is drivers, GPU, DRM. And it is responsible for interfacing with GPUs. Every laptop will have a GPU for you to draw the pictures and the graphics. And he's responsible for interfacing with the GPUs. And especially for MT8173 platform, it is using a PowerVR GPU by Imagination. I'm not sure if you ever heard of it, but actually the PowerVR is very widely used by the tablet. But actually not many laptops is using it. So I guess I still have a chance to find some new bugs, because not many laptops are using it, and maybe so I'm the first one to do some research on it, so I can find some bugs. So DRM actually provides accessible DEV paths, and there will be card 0, card 1, card 2 if you have multiple video cards. And it is accessible for normal users. That's important. If it's not accessible, you cannot attack it. So it exposes an I/O control interface for users. So normally the DRM subsystem will provide public commands handled by this function, the DRM I/O control. And you can see it is its definitions. There are lots of I/O control handlers, and but we have no permission to request the commands with these special flags. And you can see, for example, the DRM root only, DRM master, and DRM mouse. If the commands has been set these flags, you cannot access it as a normal user. You need more privilege to access it. So I have to say the public commands is not a very good attack surface for us, because we cannot access most of them. So what's next? Is it still possible to attack it? Actually, it is. So we still have another way. So we should know that the DRM supports private commands by vendors, because the public commands is provided for all GPUs, and you may find But there are still some private features for different vendors. It need to provide the private handlers. So when the number of command is larger than this one, the DRM command base, it will be the private commands handlers area. Okay, I still have 20 minutes to go. So let's take a look at the private handler on the S330 Chromebook. So there will be two private handlers. One is MTK I/O controls. Another one is PVR DRM I/O controls. So for this time, we just focus on the PVR DRM I/O control. So this function actually handles a special command that is PVR SVR KM CMD. And this command will accept a structure. It's a parameter. So the structure includes two members, which are very important. The first one is bridge ID. The second one is bridge function ID. The bridge ID has a range. It's from 0 to 24, which means there are 25 bridges in total. And for the bridge function ID, each bridge may have multiple function handlers. So the bridge function ID represents which function you want to call. So hundreds of functions are handled by this handler in total. And that is exactly the attack surface I want, because all the functions, all the features, and all the source code was provided by the vendors. They are not available in Linux upstream, but it's available on Chromebook. So okay, we just confirmed the attack surface. It's awesome. So what's next? It's time for me to build a fuzzer. So first of all, I need to recompile the kernel and flash it to the Chromebooks to enable some sanitizer like KASUN and K coverage. And this stuff can help me recognize bugs easily. And I need to define the fuzzing rules targeting the PowerVR interface, PVR, SVR, KM, CMD. So on this stage, I just told the fuzzer what the target is and how to fuzz it. Then I just need to run the fuzzer via the SSH and wait for one night. So during my wait, I can do something else, just relax and maybe play some games on PS4 and just wait, because there is nothing more I can do. I just wait the fuzzer to finish his work, and let's see if we can get some crashes or not. Luckily, I just found lots of crashes, and this is one of them. So by analyzing the stack trace is here. So this is the stack trace. And by analyzing the stack trace, I know that the vulnerable function may be this one, the PVR, SVR, bridge, sync, prim, OP, create. So if you want to access this function, you just simply set the bridge ID to 2 and set the bridge function ID to 8. Then you can call this vulnerable function. So the root cause of this bug is that mischecking the buffer size coming from user input, which may lead to integer overflow. And the yellow one is a variable came from user's input. You can control this pointer, and this pointer points to a user buffer. And so it's just an integer overflow, but after I analyze it, I know that it's able to convert this bug to a heap out of bound write, then achieve the arbitrary memory overwriting. So let's just look at the vulnerable code. First of all, there is a variable that is the UI32 buffer size here. And he firstly needs to calculate this variable. And you can see that all these variables came from the user space, so you can control it. but this function didn't check these parameters, so it's able to overflow this integer. And so if the integer is overflowed, so you can allocate a much smaller buffer than expect. So this function, the os_alloc mem no states, will alloc a buffer, and this is the pointer of the buffer, p_array args buffer. So on the last, you can see that he will call the OS copy from user. So this function will copy the user buffer from user space to the kernel space. And he will copy a bigger buffer to the much smaller kernel buffer, that is heap OOB write. So we just simply convert the integer overflow to a heap OOB write. So this page will explain how to exploit heap OOB. So there will be 2 buffers, and each buffer size is 2,000 bytes. The first one is p_array args buffer. It's the victim buffer. And the next one is IO vector array. It was made by heap spray. So hopefully it's just after the victim buffer, so it's just here. So then I'm going to use the bug to override the first IOV base. And hopefully we can override the IOV base here. So originally the IOV base is a user space pointer, but after overwriting it, it becomes a kernel address. So the next to do is just write the pipefd to copy the user buffer to the kernel address, because normally it will be copied to the real IO vector base, but after we overwrite it, we can copy the user space buffer to the kernel address. So in this way, we just achieve the arbitrary kernel address overwriting. But there's still a problem. My first version of this exploit is not very reliable, so the kernel may crash in 50% possibility by a kernel feature which name is hardened user copy. So that happens when my heap spray failed, and the kernel function copy from user will override some small heap slots. So in this picture, you can see that the first one is the p_array args buffer, is the victim buffer, no problem. But the next one is kmalloc 128 but buffers. It's not my sprayed buffer, it's something else by random. So when this happens, it will copy the buffer to a very small object. He will copy 2,000 bytes to a buffer which only has 128 bytes. So the kernel will know that, and kernel will panic by the hardened user copy feature. So what is the hardened user copy? So normally, it's a mitigation contributed by the Linux community, and it was introduced in Linux version 4 or maybe 4.5 or 4.4 or maybe later. But since the Google Chrome team has already backported it to the Linux 3.18, so it's enabled on the Chromebook. It's very annoying, but we need to bypass it. So you can see there is a boundary check in the function copy from user and copy to user by the instrumentation. The copy from user will firstly call the check copy size to check if it's a vulnerable attack or it's a normal call. So it will goes to this function, and this function will do many check. And if it copy a larger buffer to a small buffer size, and it will crash. How to bypass it? Actually, bypassing it is quite simple, because previously I copy a very large size, the 2,000 bytes to the object 128, but actually copying 20 bytes is good enough for me to override the IO vector base. So this time, I just copy only 20 bytes, and you can see that is the content I copied. The first two are 0, then I copy the kernel address and the length of the L vector. That's good enough for me to overwrite the kernel memory, and it will not crash anymore. Even I failed to spray the heap, I still got another chance to try again. So that's good enough for me. So that's all about the exploitation, but I'd like to show you a demonstration of this kernel exploit. So let's just take a look at the video. So we just start the video. So you can see it's in the guest mode. In this mode on Chromebook, you cannot install any application and you cannot install any plugin of Chrome. It's just a simple browser. What you can do is just browse the internet, maybe watch a video or something. So, but we just enable the developer mode. So this time I will not show the full exploit chain. I just show my own kernel exploit. So I will enable a shell. And I'm going to execute my binary. At this part, I just need some time to spray the heap. And just only maybe several seconds, I made it. And a root shell just shown up. And you can see I just got the root privilege of Chromebook. Thank you. Oh, sorry, not this page. OK, so that's the demonstration. So that's all about my talk. I have to thank you for your coming. I also want to thanks to the interpreter for helping me to translate it. And here is my Twitter ID and GitHub ID and my Gmail. If you have any question, feel free to ask me or just contact me. If you have any interest in something like Japanese culture or anime or something else, I'd like to talk with you about it as well. And there is a QR code. You can scan it and follow me on Twitter. Thank you. That's all.